Hello and welcome to this video. In this video, I'm going to finish chapter 1 by some concluding remarks about the Monte Carlo methods. So, we already know that one way of approximating an integral or a mathematical expectation is to use Monte Carlo methods. Okay? So we have to generate a large number of random numbers, right? And use their mean to do the approximation. Okay, but the question is how large n should be? Okay, should we stop at 1,000, 10,000, 1 million? And what is the quality of the approximation? Okay, so how fast is the convergence? Okay, to answer this question, actually, we have two theorems that you learned, the law of large numbers and the central limit theorem. Okay, so consider a sequence xn of independent and identically distributed random variables with mean theta and variance sigma square. Now take the sum of the first n variables, call it Sn. The strong law of large numbers tells me that the mean value of Sn, the average of Sn if you like, converges to theta, to the theoretical expectation with probability 1. So almost surely. Okay. Now, on the other hand, the central limit theorem states that this Sn minus n theta over sigma times radical n converges in distribution, not in probability, to a standard normal random variable. Okay. So what does this mean? It means that the probability that this quantity is between minus a and a tends to the probability that the standard normal is between minus a and a. But we know there's a formula for computing this probability, okay? Because we know the PDF of a standard normal. So it's 1 over radical 2 pi times the integral from minus a to a of e minus x squared over 2. And if you call an antiderivative of e minus x squared over 2, it's not computable actually in terms of elementary functions, but it has a name actually. We call it phi, and it has tables. It's built in all programming languages, so you don't need to worry about it. So this is just actually the difference. This is the fundamental theorem of calculus. So phi actually is an antiderivative of this exponential. So the theoretical probability is phi of a minus phi of minus a. And how to compute that? The old method is to look at tables that exist in most probability books and statistics books, but we don't need that anymore because we have softwares and it's implemented. Okay, so it's just the CDF of a normal. Okay, now what does this mean? Is if, for example, you want a probability of 95%. Okay, as you may know from previous courses, the probability that the standard normal is between minus 0.96 and 1.96 is about 95%. Okay, and this is something that you used to find from tables. Okay, it's known actually. If you want a better precision, actually 0.9, you have to take a bigger one. Okay, but it's all these are standard results actually. So with probability 0.95, the absolute value of this random variable is less than 1.96. And this the same as here actually. Okay. Now, so if we divide by n, we get Sn over n minus theta divided by sigma divided by radical n is less or equal than 1.96. And now if we multiply by radical n over sigma, we see that the mean value of Sn that I use to approximate theta is less than 1.96 times sigma over radical n. So this is actually which conclusion can we draw from this estimate? It means that we have convergent actually, but as 1 over radical n. So this explains why convergence is slow in Monte Carlo. Okay, so the convergence in like 1 over n or 1 over n squared is much faster. Okay, and we have also a problem here. The sigma can be very big. If sigma is big actually, so this means that the error is big. Okay. So yeah, I said that. And now let me give you just an example. If sigma equal 1, and we want an error, the absolute error to be less than 0.01 with probability 0.95, it's enough to take 1.96 sigma, which is 1, over radical n less than 1%, which means that radical n is bigger than 196, and if I take the square, I get n bigger than 38,416. Now, this is a moderate number. It's not a big deal. We can always generate thousands of in modern computers. However, consider the following example. Suppose we want to approximate by Monte Carlo the expectation of e to the 5z, where z is standard normal. Okay, let's see. Now, here we know the exact value, but let us see how n should be big in order to do the approximation. Okay, so it's a large number. So theta is a large number. It's 268,337. So the variance, however, is a huge number. The variance, as you may check, actually, just go back to the definition or just do the computations. You can check that the variance, the exact variance, is e to the 50 minus e to the 25. It's a huge number, actually. So if you want the relative error, just the relative error, not the absolute error, the relative error, which is actually the error divided by theta. Okay. If you want the relative error just to be 10%, if you do the computations as you did here, you will find that we will have to take n as large as 27 trillion. Okay, and for most computers, this is out of reach, actually. And even if it's within reach, it's a waste of time, actually. So this is why there are some solutions to this problem. One solution is called the variance reduction technique. Okay. Now, I don't have time to tell you about it, but this is one research problem in Monte Carlo methods, and I told you that Monte Carlo methods is a big field, actually. So I wanted just to do a small introduction, small practical introduction to these methods. Sometimes we don't have alternatives methods, so we just use simulations. Okay, because sometimes the problems that you encounter especially in actuarial science, are difficult to analyze mathematically. So this is why we do simulations. We do stochastic simulations. Okay, and I hope that I gave you an idea of how these the stochastic algorithms work. Okay, so I hope now that you have a picture of how everything boils down to generating uniform random numbers. Okay, so we can generate all the known distribution from the uniform distribution. Okay, this is why I started from the uniform distribution. Okay, so stochastic simulations is very important for practitioners. So if you want to go to deepen your knowledge in this field, I gave you a list of references in the lecture notes. And so this concludes chapter 1. Then next time we'll start with Markov chains. Okay, so thank you for your attention and see you next time.